part comes up.
I know, right?
We can use the pointer on the screen, right?
There we go. Very good. Where did I need the progress? Progress is the mouse. Should it just come up? You know,
Sure, yes.
we should just wait, maybe.
Oh, there you go.
Aha. Right. So, I'm Condron. What I mainly do is I'm a oceanographer, modeler, Arctic modeler, who sort of dabbles a little bit in paleo modeling as well. What I'm going to be talking about today is just some sort of an introduction, an overview of what the oceanography looks like, the circulation in the Chukchi Sea, and then I'll go on to talk about how we're developing models, high-resolution models to simulate this region, and how we're developing models for modern day and for sort of like more glacial-looking models. And then I'll sort of wrap it up by saying how this ties into maybe sediment deposition in certain regions, and I'll primarily focus on places like Bering Canyon and Herald Canyon. Okay. So there's a little let's focus or not, but you know, here we are in the Chukchi Sea, about 50 meters water depth. And there's some sort of features that are interesting, I think. So I don't get a mouse. Here we go. So Barrow Canyon here, off Barrow, and Herald Canyon over here, and that's sort of 60 meters at the top, going down to about 100 meters of depth, and in Hannah Shoal and Herald Shoal. And these features, what we'll see is that they heavily influence the flow of how the ocean circulates. So let's move forward. So in this region of the Arctic, as you know, a lot of you will know, primarily the water coming in is through Bering Strait. It's relatively warm water. We'll look at this a bit more, and it's quite fresh, and especially in the summer. And it's got a transport of about 0.8 spur drops, okay, and that's 800,000 meters cubic meters per second, okay. And then that water, what we'll see is that it's going to split primarily into sort of 3 branches, and where the branches go is highly dependent on the bathymetry, sort of the underlying topography of the ocean. Okay, and there's some kind of interesting things about this. This inflow of water being quite fresh is estimated maybe to provide something like 50% of the fresh water to the Arctic Ocean. Okay, and there's also thoughts that because this water is quite fresh, it's maintaining the halocline further offshore in the Arctic. And this, if you don't know what that is sort of, you know, the insulation in the Arctic where the sea ice sits. It's the cold air above the warm Atlantic water below. It's sort of the loft insulation in your house, but almost in reverse, I guess. Like a cold cellar for storing carrots. Okay, or not. So anyway, and then we go back. So there is a seasonal sort of signal to the inflow through Bering Strait. It's weaker in the winter and it's stronger in the summer. Okay, I'll talk a bit more about that in a minute. And so we can add a few more arrows in. Things start to get a little bit more complicated. And then there's little estimates have been done on what the transport is through various regions. So we look at Herald Canyon, and that's 0.3 spur drops, so 300,000 meters cubic meters per second of water. They estimate that about 0.2 spur drops is going through the middle, the central channel, and roughly about another 0.3 going down through Barrow Canyon. So you can add that up, you know, these are just rough numbers, but if you add them up, you can go get 0.8. It's not to say that that always adds up over time. And let's see, and so what happens then? So we believe that the water is basically traveling through these canyons and through these regions in very narrow currents, and they go descending down the canyons, and then there's belief that there is a sort of flow then to the east, a shelf break jet or a shelf break current. At least this is what the models are showing. There's sort of debate about whether this is real. We see it sometimes with floats and drifters, but also we've also seen, you know, floats and drifters going in the opposite direction to what, you know, dynamic we would expect. Okay. Further offshore and at depth, we'll see warm Atlantic water coming in, and then flowing in the opposite direction to this sort of eastern jet offshore, is the Beaufort Gyre, okay? And that is a sort of And the Arctic is it's about anticyclonic, and it's a sort of freshwater storage region. Let's see if I cover everything there. So look at the sort of physical water properties in this region, and it gets quite warm compared to the rest of the Arctic, especially in the summer. And it's because this region of the Arctic, the Chukchi Sea, unlike the rest of the Arctic, this region essentially looks like the sort of northern Pacific, because everything's coming northwards through there. Its characteristics are more sort of Pacific water than they are Arctic water. And in the summer we could be getting temperatures up to sort of 10 degrees C. And then as we move offshore and we get closer to the edge of the sea ice, we're getting down to sort of near freezing point. Okay? This is a sort of an average of data for 1 month, actually September 2007, which was the especially low ice year. And you can see the warm water there, and this is a sort of a snapshot from a very high resolution satellite image. I mean, it's not quite so easy to see because a lot of it was under cloud, so warm water coming in through here. But you can see very nicely going down through the Barrow Canyon, this warm water is just sort of funneling down the canyon, okay, or where the canyon is at depth. And this warm water is a heat source to the Arctic, and so there are some estimates that it might be 20% of the oceanic heat to the upper part of the Arctic Ocean. And there's also discussion, now that the receding ice in the Western Arctic is perhaps driven by a warming and intensification of flow through Bering Strait. So if we were to do like oceanographers like to do sort of cross sections of transects through water columns, and so the dots that you'll see up there are hydrographic transects starting sort of Wrangel Island and moving across towards Barrow, and at the point the dots up there on the map, they'll drop some instruments down and they'll look at what the structure of the water looks like, and interesting things are what is the salinity of the water and what is the sort of temperature, and you'll see there are sort of, I've just presented 93 and 95, but there are sort of variations from year to year. But what we're seeing is tend to be seeing warm water at the surface that's quite fresh, and then with depth you're maybe seeing a cooler water mass, which is called a winter water mass. We'll talk about that in a minute. Okay. And actually, you can just see this actually covered Harrow Canyon, this transect. So in winter, obviously it cools down. It was maybe 10 degrees C in the summer, and then getting down towards freezing point. Sea ice then occupies this area. A cold, salty water mass forms partly as a result of sea ice forming in this region. It's called this winter water mass. It's very dense and sinks. Actually, it can over time sort of occupy a large portion of the Chukchi Sea. And so we can look at flow through the canyon. We'll look at Harrow Canyon, then we'll look at Barrow Canyon. Okay, and there's sort of a number of hydrographic surveys that are done across the canyon, and they have sampling again for the water properties going through this region. And it roughly takes about 3 months for what comes through Bering Strait to make it down through the canyon. Okay, that gives you an idea of the sort of vection timescales in this region. And what happens is, the water that goes from the top of the canyon down the canyon to depth, it sort of undergoes certain changes, and we'll see that in a minute. Okay, so this is a cross section focusing on transects 2 and 3. Sorry, 2 and 4. The bottom one is section 2. What you'll see, the colours show the temperature of the water, and the contour lines show the speed of the water. When the contour lines are solid, it means that the water is going down the canyon, and when they're dashed, it means it's actually flowing in reverse. What you see at the top of the canyon is a cold water mass on one side, on the western side, and a sort of faster flowing, warmer water mass on the eastern side. And the warmer one is the sort of summer water, and the colder one is this winter water, which was formed during the winter, which by the sea ice, etc. As we go down the canyon, what we find is that this colder winter water mass actually ends up occupying a larger portion of the canyon. Okay, so a lot of this work is by, I should mention, it's not actually my work, it's by oceanographers such as Bob Pickard and Tom Weingartner at UAF. They've done a lot of work in this area. So what we're seeing is this sort of change, this sort of evolution, mixing of the water as it goes down the canyon. And then you can do the same sort of thing for Barrow Canyon. Barrow Canyon is primarily, what's flowing through Barrow Canyon is primarily supplied by the Alaska coastal current, a narrow coastal current that basically winds its way up through the Pacific, around the coast of Alaska, into the Arctic through Bering Strait, and then follows the contours down through Barrow Canyon. And so there's been a number of surveys done in this region as well, and you can make like similar plots to what we saw for Harrow Canyon, where you can look again at the temperature of the water and like the velocity of the water, okay? And you see, let's see, if we start at section 4, which is the top of the canyon, and when you're looking at through the section, you just imagine you're actually looking down the canyon, standing at the top, looking down through the water. And you'll see this depth, you see this kind of this colder winter water on the more on the eastern side, sorry, on the western side. And then as we go further down the canyon, this cold winter water now seems to occupy a larger portion of the flow there. And then, so Barrow Canyon, it has a seasonal variable flow, and it's actually linked to the seasonal variations through Bering Strait. So again, in the winter, when Bering Strait is kind of slower and weaker, there's less water going through Barrow Canyon. In summer, when there's more flow going through Bering Strait, the flow through Barrow Canyon is also increasing. Okay. I'll just say something very briefly about sea ice. You know, in winter, this area is essentially covered with sea ice, and in summer, as we were just something that came up briefly just a minute ago in one of the talks was that the Chukchi Sea used to in the summer have much more ice cover than it does now. What we've recently seen compared to the 80s to the 2000s, where now we have the Chukchi Sea, where the ice is essentially very far offshore. This is going to have huge changes, ecologically, nutrients, probably even for the sort of deposition of material to the seafloor. Okay. And it appears that this warming is not from Atlantic water, which is what some of us might have thought, but maybe it's from a Pacific warming source. So now we're sort of done with that, I'll just say briefly a little bit about what I do as a modeler. It's very high resolution models, and I'm very interested in realistically reconstructing the circulation on the in parts of the Arctic and Chukchi Sea. We have this model, it's 1/6 degree globally, and it's fun because you can take little parts of it and you can run them separately as sort of standalone models, and we're now up to 1/25 of a degree, which is 4 kilometer grid resolution. And we also have, so we have a modern day configuration, and we actually have a sort of more glacial looking configuration. Okay, and we can play around with these and see what circulation looked like in the Arctic during different times. And so, if you're thinking, wow, 4 kilometers, that's cool, and I thought, yes, that actually is pretty cool, because when you have a look, for example, at what Barrow Canyon and Harrow Canyon look like in the model, they look like this, and they look quite good. They were actually capturing the, what the seafloor looks like in that region very well, and that's massively important if you want to accurately simulate how the flow is in that region. As you go higher, coarser resolution in models, the seafloor, for example, becomes smoother, and you lose these topographic features, and as a result of that, you won't accurately simulate ocean circulation in those regions. So, if you look at Barrow Canyon and Harrow Canyon, it does a 4 kilometer resolution. It's looking quite good, and sea surface temperatures too in this region. This is for August, and 4 kilometer resolution. We're seeing something that looks pretty realistic. Okay, we're seeing warm water coming in through Bering Strait. We're capturing flow here around Barrow, where Barrow Canyon is, and we're getting sea surface temperatures roughly about what we expect, around about sort of 8 to 10 degrees in the summer. And if you look at the flow speed in the model, it's just like one snapshot, and what you'll see is that this is Harrow Canyon, this is the central channel, and this is Barrow Canyon, and we'll see that in the model the flow is sped up, it's faster there, and it's because of the fact that the model is resolving at depth these features. And one thing I'd be interested in doing as part of this sort of project, we are developing, for an iceberg project that I work on, we're developing a sediment model and a sediment deposition model, and with the idea that you could use a high resolution model that had sediment in it to look where on the seafloor your sediment would be deposited, and from a sort of drilling perspective, it might give you an idea of maybe where to look to drill, or also maybe you could run this model to tell you once you've been to a site and you've drilled it, you could use this model to sort of shed light on the characteristics of the sediment you're seeing in that region. based on how my model, say for example, deposited sediment into that region. The final thing I'll just mention briefly is that I'm interested in meltwater pulses as well, and are meltwater pulses detectable in the Chukchi Sea? We did some experiments where we were interested in young dry ice meltwater pulses, and we had a meltwater pulse coming out of Mackenzie River, which is where the red arrow is. And actually what we saw after time was that some of this freshwater was getting into the Beaufort Gyre and was heading around towards Chukchi Sea area. And so it'd be interesting to think about whether from some sort of reconstruction you could see evidence of these sort of meltwater pulses, not necessarily younger dry ice, but other ones too in the past. Okay, so I'll just end there, but so sort of 4 or 5 points. One is that it's quite a complicated region dynamically, in terms of its circulation. It's relatively poorly sampled modern day. There's not been that many research cruises going to this region. Our understanding of how the circulation works isn't very based off that much data, and it does seem we're still not entirely sure what the sort of interannual variability is in this region. Okay. The high resolution models, like I'm working with up to 4 degrees, 4 kilometers, so might help us have a better idea of what flow looks like in this region. And I should say, possibly, if you were interested in sediment modeling, you would be able to maybe shed some light on how material is deposited in these regions. That's it.
Any questions for Ellen?
I have a question. Why are the canyons there, or why do they go there? Is it because of the underlying geology, or is it because of some kind of flow, the desired path of the?
Why the canyons, where they are, or why?
Yeah, why are they there? Like it seems like sort of like specifically the Barrow Canyon seems like a sort of an odd place to how the flow sort of rides along the coast of Alaska. Then.
Right, no, that's that flow that you see is typical. It's this sort of this topography of ocean bathymetry. Essentially it guides the ocean flow. So what you'll see in the ocean a lot, not just here. You'll see what is called coastal boundary currents. Okay, you see them around, like you see the East Greenland current, the Labrador current. They're fast-moving currents that hug the coast. The Alaska coastal current is just another example of that. So it's very heavily influenced by the topography and the bathymetry of the ocean. And so that's why the water sort of likes to follow. You see what I'm saying?
As far as I understand, in modern conditions, the waters that down the troughs, down these canyons, they do not penetrate deeper than the halocline, right? So normally they go down to the bottom of the halocline. Do you see a possibility for these waters to go further down into deeper waters under some circumstances? For example, if there is a high mixture of sediment, it's like a slurry.
Yeah, right. If you had a sort of sediment loading, you often talk about these sort of sediment plumes going into depth. You can imagine, if you have a very sort of turbid, sediment-rich water mass, I think so. It would increase the density. But it would be interesting. So that's something it's something that's, from a modeling point of view, is people are only just starting to think about. But if you wanted to model, you have to put sediment into your water.
We have some evidence, some data we were measuring the neodymium isotopes in the superficial sediments on the shelf and off the shelf. And we have a feeling that there was more transport of sediment further down to the very bottom waters than it's actually observed in oceanographic evolutions.
Mm-hmm. Well, given how the Amerasia Basin is a closed basin, but the deep waters are oxygenated, it seems there has to be some kind of exchange driven by ice formation to explain that. I mean, that's always been my take on it. But I'm not an oceanographer, nor do I play one on television. So, we've got plenty of time. Any more questions for Alan?
I'm just curious what the components of your sediment transport model are.
What they would be?
Yeah.
That's a good question. Maybe it's something you could help me with. But I mean, we're developing it right now for icebergs from an IRD more of an IID perspective, which is actually a lot easier because you can just assume that maybe the material just deposits straight through the water. But for this, you would need, based on the flow, for example, and your grain size, this thing depends on how, if the material is still suspended, right? So under certain flow regimes, particles, as you slow down, big particles start to rain out, right? So that's essentially how the relationship would work. It's a sort of flow versus grain size.